Today's topic of discussion is undamped vibration of rotor on rigid bearing support. In this discussion, I will tell about how the rotor vibration equations are derived, and we'll also discuss about the derivation of critical speeds, and we'll also see the undamped vibration amplitude of rotor, and lastly we'll also discuss about the analysis of undamped critical speeds. So let's start the discussion. Undamped vibration and critical speed of rigid bearing support. What are the main points to be discussed in this section? Bearing is considered rigid, hence no displacement of shaft at bearing, and also bearing has no displacement. So these are the assumptions for the rigid bearing support. Damping of the shaft is not considered as it is assumed undamped condition. Derivation of critical speed for undamped condition and derivation of amplitude of shaft for undamped condition. Then we'll also see the curve and graph of speed versus amplitude curve or amplitude of rotor, and amplitude is infinite at critical speeds. And lastly, the undamped critical speed analysis. This is the first section is expression of undamped vibration, and this is a rotor. This is a bearing is considered rigid. That means bearing number 1 and 2 has no displacement, as well as a shaft at this bearing locations, two locations has no displacement. Mass M is attached to the shaft at center, and eccentricity of rotor is EU, and the vibration in X and Y direction is shown, which is perpendicular to the axis of the shaft. The further, let us assume the following. This is now undamped vibration of rotor. Mass at center of the shaft is m kg. Stiffness of shaft is equal to K1 Newton per meter. Eccentricity of mass from the center of axis is equal to EU in meter. Angular speed of the shaft is omega radian per second. Angular displacement in time t second is equal to omega t radian. Lateral displacement in x and y for xy axis respectively. And then equation of motion of the shaft for Cartesian form, that is m dot x double differentiation plus k1 into x is equal to m into EU omega square cos omega t, which is for x axis. Similarly for y axis or y direction, m into y double differentiation plus k1 into y is equal to m into EU into omega square sine omega t. If z is the complex number, then equation of motion of shaft for complex number form, we can write m into z double differentiation plus k1 into z is equal to m into EU into omega square into bracket start cos omega t plus I sine omega t bracket close. But e to the power I omega t is equal to cos omega t plus I sine omega t. Then we can write m into z double differentiation plus k1 into z is equal to m into EU into omega square into e to the power I omega t. So this is expression for motion of undamped vibration of rotor. Now undamped critical speeds. Now we have to find out the how the expression is derived for undamped critical speed. Equation of motion of shaft for the complex form, just now we have seen m into z double differentiation plus k1 into z is equal to m into eu into omega square into I omega t. For natural frequency, external force will be 0. That means this term will be 0. So we can write m into z double differentiation plus k1 into z is equal to 0. This is equation 1. Assume the solution of the form z is equal to z1 into e to the power lambda t, where z1 is a displacement or amplitude in complex number, lambda is eigenvalue, and t is a time. So z double differentiation is equal to z1 into lambda square into e to the power lambda t. After replacing z and z double differentiation from the equation 1, we can write bracket start m into lambda square plus k1 bracket close into z1 into e to the power lambda t is equal to 0. But z into e to the power lambda t cannot be 0, and so we can write m into lambda square plus k1 is equal to 0. So lambda is equal to plus minus I bracket start, sorry, lambda is equal to plus minus I into square root of k1 upon m, where it has two eigenvalue. Lambda 1 is equal to 0 plus I bracket cubic of sorry, square root of k1 upon m. Similarly, lambda 2 is equal to 0 minus I square root of k1 upon m. So we have two eigenvalue. So forward undamped lateral natural frequency is plus square root of k1 upon m, and backward undamped lateral natural frequency is equal to minus square root of k1 upon m. So undamped critical speed omega cr is equal to plus, that is forward, plus square root of q1 upon m. So this is expression of undamped critical speed, which is in radian per second. If you want to convert in rpm, we have to multiply wcr into 60 upon 2 pi. So this is expression for undamped critical speed of rotor. Now undamped vibration amplitude. Equation of motion of the shaft for the complex number form, we can write m into z double differentiation plus k1 into z is equal to m into eu into omega square into e to the power I omega 2. So this is equation 2. After assuming the solution of the form z is equal to z1 into e to the power I omega t, where z1 is displacement or amplitude in complex number, t is the time. So z double differentiation is equal to z1 bracket start I omega to the power 2 into e to the power I omega 2. So z double differentiation is equal to minus z1 into omega square e to the power I omega t. So after replacing z and z double differentiation from equation 2, we can write bracket start minus m omega square plus k1 bracket close into z1 is equal to m into eu into omega square. So z1 upon eu is equal to m into omega square upon bracket start minus m omega square plus k1 bracket close. So after dividing above expression with k1, we can write z1 upon eu is equal to omega square upon bracket start k1 upon m bracket close upon bracket start 1 minus omega square upon bracket start k1 upon m. But k1 upon m is equal to omega cr square. So we can write z1 upon eu is equal to omega upon omega cr to the power 2 upon 1 minus omega upon omega CR to the power 2. If frequency ratio F is equal to omega upon omega CR, then we can write Z1 upon EU is equal to F square upon bracket stand 1 minus F square. Let's say amplitude or magnitude of Z1 is A1, then A1 is a displacement or amplitude from 0 to peak. So we can write A1 upon EU is equal to F square upon bracket start 1 minus F square bracket close. So when frequency ratio is equal to 1, that means the speed omega exciting frequency is equal to critical speed frequency, that is omega CR, and so amplitude at the resonance is infinite because F is equal to 1. So this is A1 upon EU is equal to infinite. So resonance or amplitude becomes infinite when omega is equal to omega CR. That means exciting frequency is equal to natural frequency, or critical speed is equal to exciting speed. Now the undamped vibration speed versus amplitude curve. So let us see, this is a typical example. We have a speed on x-axis and amplitude in y-axis, and the top, this one is a consider plus and minus both, and this one is considered only the positive value. So if this is the value, let's say operating speed is 10,000 and first critical speed is 5,000. So frequency ratio will be F is equal to omega upon omega CR is equal to N upon NCR1. So with this value we can calculate F. So after putting this value in F, we can get this data where plus and minus. So below the critical speed, amplitude is positive. After critical speed, it is a negative. But if you take the magnitude, so we can see this is both sides is positive. The most important part is at the critical speed, the magnitude is infinite. So at critical speed, you can see the 5000 RPM amplitude of rotor is infinite for the case of undamped vibration. Now same explanation. X-axis is speed, y-axis is amplitude, and you can see if you consider another critical speed, that is 8000. So you see at the 8000, before this, for this it is positive, after 8000 it is negative. If you take the both as a positive or amplitude is positive, at 8000 it is infinite. So if you consider the both, that means first critical and second critical speed. So on x-axis is speed, y-axis is amplitude. So at 5000 it is becomes infinite, and 8000 it is become infinite. So we can say the critical speed or resonance, at a resonance the amplitude of rotor is infinite. Now the undamped critical speed analysis. Let's say this is a typical example. Critical speed NCR1 is equal to 5000 and another is NCR2 is 8000 RPM. Exciting frequency is equal to operating speed, which is suppose 10,000 RPM. So first critical speed, separation with respect to first critical speed in percentage, we can calculate operating speed minus first critical speed bracket close into 1000, so into 100 divided by operating speed. So we can calculate it is a 50%. So for the first critical speed with respect to design operating speed, the separation or gap is 50%. For the second critical speed, which is 8000 RPM, same way we can calculate separation, it is 20%. So as a separation of operating speed, that is exciting speed, with respect to first and second critical speed is above 15% and so safe for operation. Additional notes: if the machine is operating with more than one rotor, each rotor is having separate critical speed and its individual speed of rotor is treated as exciting speed. There will not be resonance of critical speed of the first rotor with respect to exciting speed of another rotor or vice versa. So each rotor is treated separately for critical speed analysis. So I hope you have understood about the what is undamped vibration of rotor, how expression for motion for undamped condition is derived, and how the derivation of undamped critical speed is done. Then what are the graphs showing at maximum or infinite at a resonance condition, that means at critical speed becomes equal to operating speed, that time the amplitude is become infinite. And lastly, you have to understood there should be separation between the exciting speed and the critical speed, and it should be above 15% for the safe operation. So thank you for watching.